Welcome to our first lecture in organic chemistry. As you can see here, we are starting at chapter 10 in your textbook, which is organic chemistry. So hope you all had a good winter break and back for the spring semester and all ready to start working hard at organic chemistry. So let us begin our lecture. As I mentioned, we're dealing with organic chemistry this semester. So let us first of all get the perspective of organic chemistry. So historically, organic chemistry can be dated back to 1828, when Wöhler carried out a set of experiments and he made a compound that was known at that time as urea. And that was known to be an organic compound. So we'll have to define organic compounds in a second. But the main thing here is that he carried out this reaction using two salts, ammonium chloride and silver cyanate. Those are salts and they are classified as inorganic salts. But he carried out this reaction and made urea, which is organic. So now we'll have to define organic compounds and organic chemistry. So organic chemistry is the study of compounds that contain carbon. So here's a key word. All of the compounds that we will be studying for this semester will contain carbon, and that makes it organic. So organic chemistry is the study of compounds that contain carbon. It turns out that organic compounds are made up of carbons and other elements. These include mostly hydrogen. So the large percentage of organic compounds contain carbon and hydrogen. Some contain oxygen and nitrogen, and others contain sulfur, phosphorus, and the halogens. So what I want you to do is to get out your periodic table and find carbon on the periodic table. You'll see that it is to the right on the column 4. What you will notice is that all these atoms here, or these elements here, hydrogen, oxygen, nitrogen, sulfur, phosphorus, and halogens, they are all to the right of the periodic table. So you may want to pause the video and get your periodic table and find these elements. They're all in one area of the periodic table. What you'll discover in organic chemistry is that we have terms that you'll have to get familiar with. So we will communicate by using these terms, and you will have to understand the meaning of these terms. So one of the first terms that we'll mention here is the term heteroatoms. Hetero here means different, and of course atoms. So heteroatoms are atoms that are different from carbon. So, well, carbon and hydrogen. So oxygen is considered a heteroatom, likewise nitrogen, likewise sulfur, phosphorus, and halogens. These are all referred to as heteroatoms, and organic compounds contain carbon and mostly hydrogen, and some contain heteroatoms. So don't get confused. When we use the term heteroatoms, they are atoms that are different from our carbons. As you can imagine, the combination of carbons with hydrogen and the other heteroatom, there is the possibility of literally millions of different organic compounds. As you can see here, about 10 million compounds are estimated, and chemists are making approximately 100,000 new organic compounds every year. And that's just organic compounds. That's just compounds that contain carbon and other heteroatoms. So a lot of compounds that exist, including the pharmaceutical compounds and other cleaning compounds, are all organic, and there are a lot. Also, biochemistry. The carbohydrates and the lipids and the proteins and the enzymes, etc., are all considered organic. Why? Because they all have carbons. So our job is to understand the chemistry of all these organic compounds. As you can imagine, we won't have time to identify all 10 million compounds and study each, but what we'll do is we will find a way to categorize all these organic compounds and study them in different categories. So that's the approach that we'll use in this course. So here's an example of two organic compounds that you are very familiar with. This one is DEET. It's an insect repellent. And of course, as you can see, this one is a painkiller, ibuprofen. You'll notice here that there are no carbons. That's written. And I put this here to show you that before the semester's out, you will be comfortable drawing these compounds and understanding the meaning of these different drawings. So what's shown here, a bunch of lines, and you can see here O for oxygen and N for nitrogen. So those are the heteroatoms. However, you do not see any carbons because carbon is a part of every organic compound. We do not show it as C. We just put a intersection. So at each intersection here is a carbon. So don't worry too much about that. I put this here specifically to illustrate to you that we have different ways of representing organic compounds, and before the semester is out, you should be familiar with these different ways. So let's get back to basics. So, organic compounds differ from other compounds, which we'll describe as inorganic compounds, in different ways. Organic compounds have mostly covalent bonds. You may remember from your Gen Chem that covalent bonds are bonds in which electrons are shared. So in other words, the bonds that are formed for organic compounds, they are formed with elements in the same region of the periodic table. As I pointed out earlier, it's mostly carbon, nitrogen, and oxygen, and the halogens, they're all in that same region. In contrast, ionic compounds are classified as inorganic. Sodium chloride, for example, is inorganic. Look at the periodic table. You see sodium to the extreme left and chloride to the extreme right. That's inorganic, which are described by ions held together by their charges. Organic compounds are mostly gases and liquids. Some are solids. Inorganic compounds are mostly solid with high melting point. Just think of sodium chloride. The melting point of sodium chloride is extremely high, but the melting point of most organic compounds tend to be low, as you can see here, much less than 360 degrees C. Most organic compounds are insoluble in water. Most inorganic compounds are soluble, such as sodium chloride, for example. One example over here is for the organic compound is oil. Oil, of course, as you know, is organic because it consists of carbons and hydrogens. That's insoluble in water. And we won't go into the rest here, but these are, in fact, the most important ones to differentiate between organic compounds and inorganic compounds. Okay, let us look here at how we communicate the structure of organic compounds. As you can see here, methane, it's CH4. So it's organic because it has carbon and, of course, 4 hydrogens. But in organic chemistry, we will not just say CH4, we want to communicate the structure of CH4. What does it look like? So what you studied in Gen Chem is the Lewis dot structure. So you may want to go back and review Lewis dot structures. The Lewis dot structure of CH4 is given here, where these electrons here are the bonding electrons, shown by dots, and that's why it's called a Lewis dot structure. Electrons are represented by dots. So this is the Lewis dot structure of methane, where these electrons here are the bonding electrons between carbon and hydrogen. So the bond between hydrogen and carbon has 2 electrons, and that's called a covalent bond. Here's another example. We have here carbon dioxide. So here's CO2, carbon dioxide. It's organic because it has carbon. It has 2 heteroatoms here, which are oxygens. Notice the term, heteroatoms, so don't get confused. Here is the Lewis dot structure. Notice again from your Gen Chem course, there are 4 electrons between carbon and oxygen. And those are the covalent electrons, or the bonding electrons, making a covalent bond. So here we can represent the covalent bonds by lines. So now you see why in the previous slide that I gave you, we had lines. So in organic chemistry, we use lines to represent the bonding between 2 atoms. If it's if there are 2 lines, that's a double bond. And if, of course, as we did with methane, if there's 1 line, it is a single bond. So you have to be familiar with drawing Lewis dot structure and drawing the structures of organic molecules. Here's some more examples. Here's the molecular formula. CH2O of an organic compound. Why organic? Because it has carbon. And of course hydrogen and the heteroatom oxygen. But as you can imagine, CH2 does not give us an idea of the structure of this molecule. So to get an idea of the structure of this molecule, we can draw the Lewis dot structure. And here it is, the Lewis dot structure. So you'll have to take into consideration the number of valence electrons. So once again, you may have to go back into your Gen Chem course to review Lewis dot structure. So this is the Lewis dot structure of this molecule here. Here is another way of drawing it that you will be more familiar, that we will use a lot in this course, and it's called the structural formula, where we're using lines to represent bonding electrons. So here are 2 electrons, and here's 1 line, so that's a single bond. Here are 2 electrons, here's 1 line, and that's a single bond. Here are 4 electrons, and here are 2 electrons to represent 4 electrons or a double bond. Here we have electrons here that are non-bonding electrons, and we just include it in the structure. So this is the type structure that we will use to represent organic molecules. Here's another example. C2H4. Question now becomes, what does that structure look like? In organic chemistry, we have to get an idea of the structure of the molecule so that we can perform reactions, etc. So this Lewis dot structure is here, that you learned in Gen Chem. The structural formula is here. Again, 2 electrons, a single bond, 4 electrons here, a double bond. So this is the structural formula of this molecule given by the C2H4. So what you will observe after drawing a lot of Lewis dot structures is that carbon normally has 4 covalent bonds. 4 bonds. It could be 4 single bonds, it could be 2 single bonds and a double bond, etc. But 4 bonds, no more than 4. Hydrogen has 1 bond to it. Nitrogen has 3 bonds to it. So after drawing a lot of Lewis dot structures that have nitrogen, you will observe that nitrogen has a maximum of 3 bonds to it. Oxygen has 2 bonds. Recall that these are heteroatoms. And halogens, they have 1 covalent bond. So as I mentioned earlier, we have tens of millions of different organic compounds. So now you can see how we can start categorizing them based on similarities. One similarity that we have observed is that all the carbons in all these 10 million compounds, they all have 4 bonds to it. No more than 4. We can't put 5 bonds. If there's a hydrogen, there's only 1 bond to that hydrogen. Nitrogen, there are 3. The next slide has some examples. So, here are some examples of organic compounds. Here's ethane. Why organic? Because it has carbons and hydrogens. And this is the structural formula of ethane. You should become familiar with drawing the structural formula of compounds. So we have carbons and hydrogen. Notice this carbon has 1, 2, 3, and 4 bonds to it. As we pointed out earlier, let's look at this carbon. This carbon has 1, 2, 3, and 4 bonds to it. Let's look at this carbon in ethylene. This carbon has 1, 2, 3, and 4 because that's a double bond. So there are 4 bonds to it. So now you can see the way of categorizing the different molecules of organic compounds. Here's acetylene, the gas that's used in welding torches. So here is acetylene, here's a carbon, so therefore it is organic. It has 1 bond, 2, 3, and 4 because that is a triple bond. So 3 plus 1 equals 4. We have 4 bonds to it. Here is halogen, chlorine. And as we said on the previous slide, there's only one bond to the halogen, and here it is, one bond. Here's hydrogen. We said that there is only one bond to hydrogen, and here it is, only one bond here to hydrogen. Same here. Let's look at some others. Oxygen. We say that oxygen has a maximum of 2 bonds. So here's oxygen, here's 1, and here's 2 bonds to oxygen. What you'll discover is that when you draw the Lewis dot structure, there are 2 pairs of non-bonding electrons around oxygen. You may recall from Gen Chem, when you draw water, H2O, you draw oxygen in the middle and 2 hydrogens, and of course 2 pairs of non-bonding electrons. Here's oxygen again, 2 bonds, 1 and 2, and of course 2 pairs of non-bonding electrons. We mentioned nitrogen. Nitrogen has 3 bonds to it, 1, 2, and 3, and a pair of non-bonding electrons. So once again, of the 10 million compounds, organic compounds, all that have nitrogen, they will have 3 bonds to the nitrogen. Here's another organic compound. Here's a nitrogen, 1, 2, and 3 bonds to it. Here's hydrogen cyanide. Here's a nitrogen. It has 1, 2, and 3 bonds to it. So all organic compounds that have the heteroatom nitrogen will have 3 bonds. All organic compounds that have the heteroatom nitrogen will have 2 bonds. Well, nitrogen 3 bonds. All that have oxygen will have 2 bonds. All that have carbon, and that's all organic compounds, will have a maximum of 4 bonds. Okay, let's look at another way of categorizing and classifying organic compounds. We will use the term functional group. So let's define that. As we mentioned, organic compounds, they have carbon and hydrogen and a lot of, and some heteroatoms. It turns out that on just about all organic molecules, there are specific arrangement of atoms, specifically the heteroatoms. So we have here an atom or group of atoms within a molecule that have a specific characteristic or specific arrangement. We'll classify as a functional group. It turns out that those that have these specific characteristics, they have specific reactions that they undergo. But for the time being, we will define functional group as a specific arrangement of heteroatoms or atoms in an organic molecule. So we're going to divide up all the 10 million of organic compounds into different categories based on functional group. This makes it a little clearer because here are some functional groups. OH. I'm sure we have heard of organic molecules being an alcohol. Ethanol and methanol are fuel. So the ethanol here shows that it belongs to a family called alcohols. Why alcohols? Because all alcohols have the OH arrangement of the heteroatoms. So this is an alcohol, ethanol, because here is the OH. Amines is another functional group or another family of organic compounds. They all have the NH2. So ethylamine, here is the NH2, and here some carbons and some carbons. So this molecule here is described as an amine, and specifically it is ethylamine, but the functional group here is NH2. Here's another functional group, the aldehyde. The family is the aldehyde. Here's what it looks like right here. Carbon bonded to an oxygen with a double bond, and bonded to a hydrogen, and bonded to another carbon group over here. It's an aldehyde. So here's an example of an aldehyde. Here is the functional group C double bond OH, and it's bonded to another carbon, and this specific one is acetaldehyde. Here's another functional group, ketone. The family here is ketone. Here's what it looks like. A carbon that's bonded to an oxygen by a double bond, and bonded to something else and something else. A specific example is, here is the carbonyl, or the carbon-oxygen double bond, and this time, for this specific example, it's bonded to CH3, and the CH3 that makes it acetone. So of course, as you know, acetone is a common solvent in organic chemistry. So this is a specific example of an organic compound that has the ketone functional group. Another one is carboxylic acid. Here's what the carboxylic acid looks like. It is a carbon-oxygen double bond bonded to an OH, specifically an OH. And of course back here would be bonded to some carbon or something else. A specific example is acetic acid, where we have here the carboxylic acid functional group, and this time it's bonded to CH3, and that specific molecule is known as acetic acid. Because as you know, acetic acid is vinegar, the main ingredient in vinegar. I think vinegar is about 2% or 2% acetic acid. Here's another group, the ester. Here's what it looks like. It's a carbon-oxygen double bond bonded to an OR. I'll define OR here as a carbon group. OR is another term that's used for organic portion of a molecule, typically carbons. And we have another group bonded back here, which could be carbons. Specific example is, here is our ester right here, and here's the R group, CH2, CH3, and here is a specific CH3. So this becomes a specific molecule, and this molecule is called ethyl acetate, another common organic solvent used in industry for paint thinners and cleaning solutions, etc. So this is ethyl acetate that has the ester functional group. The last one that we'll look at is the amide. And it looks as if, in this case it has a carbon-oxygen double bond, but in this case it's bonded to an NH2. And of course bonded back here could be any carbon containing group. This is a specific example. The methyl group CH3 is bonded to this carbon, and here is the amide portion of the molecule, or the amide functionality, and this is called acetamide. That's another common organic compound. So again, these are the categories or the families of compounds that we will examine in this course, and be able to recognize them and be able to identify what are the functional groups, such as alcohol or aldehyde, in different molecules. Let us look at a different representation. Here again is the aldehyde. It has here the carbon-oxygen double bond bonded to an H. Notice the H. And the R group here is just a representation of carbon groups. Another one is, of course, the ketone. Here is the carbon-oxygen double bond, and it's bonded to two different, or could be the same, R group or carbon groups. And here's the carboxylic acid. Here it is. Here's the ester that we pointed out earlier. Notice the name. Esters are sweet-smelling compounds. Those are used primarily in the perfume industry and the flavoring industry. A lot of the flavoring that's used in industry are esters. And of course, here's another one, alcohols, ROH. We're familiar with ethanol and methanol. And here's another group, ether, that's OR. So we have R bonded to oxygen. Let's look at a couple more. And here is that we explained earlier, the amine. So we have here the nitrogen bonded to R groups. Could be hydrogen or R groups. And we didn't do this one, but amide we did here. So here is the carbon-oxygen double bond bonded to nitrogen. Could be an H or it could be another R. So again, you should be able to identify these different functional groups or these different specific arrangements of atoms in organic molecules. What we'll do for the next few slides is to examine each in details. For this one, we'll just start with the alcohols. So we have already identified the alcohols as containing the OH group or the hydroxyl group. So here is the hydroxyl group bonded to a carbon. And here is the hydroxyl group bonded to a carbon. So these are two alcohols, or two representations of alcohol. This one is a specific one where this is a CH3 and a CH2 and an OH. CH3, CH2, OH. That's of course ethanol, as we have discussed before. Don't worry too much about this. This is the model. So if you have your model set, if you built it, that's what it looks like. And not just a straight line, but it's kind of tetrahedral, as you've learned from your general chem course. What we'll do here is, still looking at the alcohols, we will see if we can classify alcohols further. Instead of just saying here's an alcohol, can we say that here is a different type alcohol from another type alcohol? Because as you can imagine, there are literally thousands of different alcohols. So let's see if we can classify alcohols even further. So here is how we can do it. Here's the carbon, here's the OH, and here's the carbon that it's bonded to. If there are only hydrogens that's bonded to this alcohol, to this carbon, and there are 4 bonds to every carbon, so there cannot be any more. So this one has 3 hydrogens in addition to the OH. That's specific to methanol. Another variation could be, here is the carbon OH again. So if we have one R group, one alkyl group, we'll classify this as a primary alcohol, usually written as 1 superscript 0. As I mentioned earlier, we have a lot of symbols and terms that we use to communicate organic chemistry. This is a classic one. where we have one superscript. Primary 1 refers to one alkyl group. As you can imagine, if you have two alkyl groups bonded to this carbon that contains the OH, it's a secondary, or 2 superscript 0. Taking that reasoning further, you will see that if you have 1, 2, and 3 carbon containing groups or alkyl groups bonded to this carbon that contains the OH, it's a tertiary or a tertiary alcohol. So your job is to look at a specific alcohol, and you should be able to determine if that alcohol is a primary, secondary, or tertiary alcohol. Knowledge of the type alcohols will be very important when we start doing reactions. So let us look at some examples here. This is, before we give the answer, let us look at this alcohol. This is the carbon that's bonded to the OH, so therefore it is an alcohol. It has 2 hydrogens and 1 alkyl group, or 1 carbon containing group, so therefore this alcohol is a primary alcohol. This alcohol here, let's do the similar analysis. This is the carbon that we're interested in, and this is the OH because it makes it the alcohol, and it has 1 and 2 carbon containing groups or alkyl groups or R groups bonded to that carbon. Therefore it is a secondary carbon. Now you can see the importance of drawing out the structures of organic molecules. And that's an important part of this course, is being able to draw out the structures of organic molecules. Let's look at the third one. Here's a carbon of interest because it's bonded to the OH. So this carbon here is bonded to 1, 2, and 3 carbons. Hence, it's classified as a tertiary alcohol. So you should be able to look at any molecule, determine if it's an alcohol or not, and you should be able to further classify that as primary, secondary, or tertiary alcohol. Let us see if we can apply what we have learned to solving a problem. So here is the question. Draw the Lewis dot structure and condense structural formulas of 2 alcohols with this formula. Okay, so you first have to think this through carefully, because we will be applying all the knowledge that we have just discussed, or all the concepts that we have just discussed. This is organic. It has 3 carbons, 8 hydrogens, and 1 oxygen. It mentioned that it is an alcohol. So we must have an OH present in the structure. And of course we're going to put some R groups back here, and this R group must have 3 carbons. And well, in this case 7 hydrogens, because we've used 1 hydrogen here. So you will have to put together a Lewis dot structure that has an OH bonded to it, because they are alcohols. Let's see. So you may want to pause the video here and get your pencil and your paper, your workbook, and see if you can draw these out. Because organic chemistry here is really you working to solve these problems by applying the concepts that we have just discussed. So we're not looking for answers here. What we want from you is, can you apply the concepts to solve this particular problem? Let's see what the answer is. So one is looking like this. So we have 1, 2, 3, 3 carbons, 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, and 8, and 1 oxygen, and here it is. Since it's an alcohol, we must have the OH group. So that's one possibility. The other possibility is down here. We still have 3 carbons, 1, 2, and 3. We still have 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, and we have 1 oxygen. But we also have here the OH because we know it's an alcohol. So we can draw out the Lewis dot structure, or we can do the condensed structural formula, which is CH3, CH2, CH2, OH. Or, for the other molecule, CH3, CH, CH3, OH. So if you are asked to classify these as primary, secondary, or tertiary, this OH is bonded to this carbon, and it has 1 alkyl group and 2 hydrogen, so it is a primary alcohol. This OH is bonded to this carbon, which has 1, 2 methyl groups or 2 alkyl groups, so therefore it is a secondary alcohol. So that's what you need to practice. Is to first of all identify an organic molecule as an alcohol, and further identify the alcohol as primary, secondary, or tertiary. What I'll do is give you some practice tutorial questions over the weekend for you to turn in next week, and this will give you more practice on solving these types of problems, or applying the concepts that we've learned in this lecture to solving different problems. I think this is the last slide, and yes it is. So once again, look out for that tutorial question sheet that will be posted in D2L over the weekend. Practice the problems in your textbook. Use these lectures and PowerPoints as supplemental material as you have your textbook right there with you, working the problems in the text. And so that's basically what is required here as we get started. So continue to work hard, and I'll post another lecture video on this chapter before too long. But look out for the tutorial questions, and I'll send out an email over the weekend in terms of having a quiz next week or not. Okay? Continue to study hard and have a great semester, and